Fire, the primal force that sparked the dawn of civilization, a tool, a weapon, a life-giver, and a destroyer. In the grand tapestry of human history, fire holds a singular and profound significance. Its discovery marked a turning point in our evolution, illuminating the path from primitive existence to the dawn of civilization. Picture our ancestors huddled in the cold, dark caves, their lives forever altered by this newfound ability to harness this elemental power. Fire provided warmth against the bitter chill of the night, warding off predators and adding an extra layer of security to our vulnerable existence. But the importance of fire did not stop at mere survival. It was also a means to transform our food, making it easier to digest and expanding the range of edibles at our disposal. It was through fire that we first tasted cooked meat, unlocking a rich source of nutrients that fueled our growing brains. As we journeyed forward in time, fire continued to be our steadfast companion, instrumental in shaping our world. It was fire that allowed us to forge metals, giving birth to tools and weapons that would redefine our relationship with the environment. From bronze to iron, each leap in metallurgy marked a new era of human development, all enabled by the transformative power of fire. Fast forward a few more centuries, and we see fire powering the steam engines that drove the Industrial Revolution, pushing us into an era of unprecedented growth and technological advancement. Fire, in its many forms, has been at the heart of human progress, a catalyst for change and a beacon of innovation. Yet, for all its life-giving properties, fire is also a force of destruction. Unchecked, it can consume forests, level cities, and claim lives. This duality makes understanding fire all the more crucial. It begs the question, what exactly is a flame? Indeed, fire has been instrumental in shaping our world. But what exactly is a flame? Let's explore. A flame, in essence, is a chemical reaction, a dance of molecules in the air. It's a captivating spectacle, isn't it? But what's really happening behind this fiery ballet? Let's start with the basics. Combustion. Combustion is a chemical reaction between a fuel and an oxidizer, usually oxygen, which produces heat and light. When you strike a match, the heat from the friction triggers the combustion of the match head, which then ignites the wooden stick. The heat from the flame continues to break down the molecules in the wood, releasing gases that react with the oxygen in the air. This is what keeps the flame going. Flames can be of two types based on the combustion process, complete and incomplete. In complete combustion, the fuel is entirely consumed, producing only carbon dioxide and water as waste. This type of flame burns with a blue color, indicating a high temperature and efficient combustion. The blue flame you see on a gas stove is a good example of this. On the other hand, incomplete combustion occurs when there isn't enough oxygen to burn all the fuel. This results in the production of carbon monoxide, a poisonous gas, and soot, those tiny black particles you see floating around a campfire. Incomplete combustion flames are usually yellow or orange, and are less efficient and hotter than blue flames. Now, what about the role of oxidizers in flame propagation? Well, without an oxidizer, a flame simply cannot exist. The oxidizer, usually oxygen, is what the fuel reacts with to produce heat and light. In a sense, the oxidizer breathes life into a flame. Let's talk about the chemical composition of flames. A flame primarily consists of hot gases. In the case of a wood fire, these gases include water vapor, carbon dioxide, carbon monoxide, and soot particles. And depending on the fuel and conditions, a flame may also contain nitrogen oxides and other compounds. So, what gives a flame its color? The answer lies in the emission spectra of the atoms within the flame. The heat energy from the flame excites the atoms, causing them to emit light at specific wavelengths. Different atoms and molecules emit different wavelengths of light, which our eyes perceive as different colors. For example, sodium atoms emit a yellow light, while copper atoms produce a green light. So when you toss a handful of table salt or a copper penny into a fire, you see a burst of yellow or green color. In conclusion, a simple flame is a complex and fascinating mixture of chemistry and physics. It's a delicate balance of fuel, oxidizer, and heat, all playing their part in the dance of molecules in the air. So the colors we see in flames are a direct result of the chemical reactions happening within them. Now that we know the chemistry behind flames, let's discuss the physics. To truly understand flames, we need to delve into thermodynamics, the branch of physics that deals with heat and temperature, and their relation to energy and work. In the context of flames, we're talking about the thermodynamics of combustion. Combustion, in essence, is a chemical reaction, typically a high-temperature exothermic redox reaction. The energy produced by this reaction is what we perceive as heat and light. But the fascinating aspect is how this energy transfers. It does so in three ways: conduction, where heat is transferred through direct contact; convection, where heat is transferred through a fluid, which in this case is the hot gases produced by the flame; and radiation, where heat is transferred through electromagnetic waves. But what's the role of fluid dynamics in flames? Well, it's all about the movement. Flames can be categorized into two types based on fluid dynamics: laminar and turbulent. Laminar flames are smooth and steady with gas flow in parallel layers. On the other hand, turbulent flames are irregular and chaotic, with gas flow that whirls and mixes. The interaction between these flames and the surrounding air can significantly impact the flame structure and combustion efficiency. Now, let's scale up a bit and consider the effects of gravity on flames. Here on Earth, gravity pulls cooler, denser air downward, forcing the hot gases produced by a flame to rise. This results in the familiar teardrop shape of a flame. But in microgravity conditions, like aboard the International Space Station, flames behave differently. Without gravity to direct the airflow, flames become spherical, burn slower, and require less oxygen. Environmental conditions also play a significant role in how flames behave. Factors such as air temperature, humidity, wind speed, and atmospheric pressure can all impact a flame's characteristics. For instance, on a hot, dry day, a flame can spread more quickly than on a cool, damp day. Similarly, at high altitudes, where the air is thinner, flames can struggle to find enough oxygen to sustain combustion. So, how does a flame spread? Flame propagation occurs when the heat from the flame raises the temperature of a fuel source to its ignition point. The fuel then begins to combust, and the flame spreads. The speed at which this happens depends on various factors, including the type of fuel, its configuration, and the surrounding conditions. The physics of fire is as complex as it is fascinating, affecting everything from the flame's shape to its temperature. Flames are not merely the result of a chemical reaction. They are a symphony of physical phenomena, combining thermodynamics, fluid dynamics, and environmental factors in a beautiful, if sometimes destructive, display. Understanding the physics of flames not only satisfies our curiosity, but also equips us with the knowledge to harness fire's power responsibly and protect ourselves from its potential dangers. The physics of fire is as complex as it is fascinating, affecting everything from the flame's shape to its temperature. Materials react differently to fire. Some resist it, while others fuel it. The flammability of a material is determined by the ease and speed at which it ignites and burns. Highly flammable materials such as paper and dry wood catch fire quickly and burn rapidly. On the other hand, materials such as brick and concrete are fire-resistant. They do not readily burn and can withstand high temperatures. The fire resistance of a material is not just about its ability to withstand fire, but also about how it responds to fire. Some materials may not burn, but they might release toxic fumes or melt, creating additional hazards. That's where fire safety gets interesting. Material science has opened up new avenues in fire safety. Innovations are constantly being made to improve the fire resistance of materials. One such innovation is the development of fire-retardant materials. These are materials that have been treated with a fire-retardant chemical or are naturally resistant to fire. They can slow down or even stop the spread of fire, giving people more time to escape and firefighters more time to extinguish the flames. Fire retardants work in several ways. Some retardants release a gas that displaces oxygen, suppressing the fire. Others form a protective layer on the material that insulates it from the heat, preventing it from reaching the temperature at which it would normally ignite. Still others cause a chemical reaction that reduces the amount of heat the fire can produce. It's fascinating to think about how these different materials and innovations can be applied in real-world situations. For example, Fire retardant materials are used in many aspects of building construction, from the insulation in the walls to the upholstery on the furniture. They're also used in the manufacture of fire-resistant clothing for firefighters and other professionals who work in high-risk environments. Understanding how different materials interact with fire is key in fire prevention and control. By choosing the right materials and by understanding how they respond to fire, we can design safer buildings, create more effective firefighting equipment, and ultimately save lives. The science of materials and fire is a crucial part of that process. Controlling a flame requires understanding how to interrupt its life cycle. Flames, as we know, thrive on heat, fuel, and oxygen. Interrupt any of these, and you've got yourself a method of flame control. First, let's talk about flame extinction through physical processes. Cooling is the most straightforward. By reducing the heat of the flame, we can actually stop the combustion process. This is why water is a common firefighting tool. It absorbs heat and evaporates, taking away the thermal energy necessary for the flame to continue. Next, we have smothering. This involves cutting off the oxygen supply to the flame. Fire needs oxygen to sustain the combustion process. So, if you deny it oxygen, you effectively suffocate the flame. This is the principle behind using a fire blanket or a layer of foam. They create a barrier between the flame and the air, preventing the fire from getting the oxygen it needs. Now, let's move on to chemical processes. Chain reaction inhibition is a fascinating concept. Some chemicals, when introduced to a flame, can interrupt the chain reaction that sustains the fire. They work by producing molecules that are highly reactive with the free radicals generated in the flame, effectively neutralizing them. This halts the chain reaction, and thus, the flame is extinguished. Fire suppression systems employ these principles in varying ways. Water-based systems primarily cool the flame, while foam systems smother the fire and cool it down. Dry chemical systems often use substances like sodium bicarbonate or potassium bicarbonate, which decompose in the heat and produce gases that inhibit the chain reaction. Carbon dioxide systems smother the fire by displacing the oxygen, but also cool the surrounding area due to the low temperature of the released CO2. From cooling to smothering, the mechanisms of flame control are diverse and intricate. Understanding them not only equips us to deal with fires more effectively, but also paves the way for creating innovative solutions in fire safety. Firefighting is an art and science that has evolved over centuries. From the ancient bucket brigade to the modern usage of advanced technology, firefighting techniques have seen a remarkable transformation. Historically, firefighting was a community effort. People would form human chains, passing buckets of water from hand to douse the flames. This method, though laborious, was a testament to the power of collective action. As civilizations grew and technology advanced, so did our methods of combating fire. The invention of the fire pump in the 17th century by Dutch inventor Jan van der Heyden was a game-changer, allowing water to be sprayed directly onto fires, a concept still in use today. In the modern era, firefighting has become a specialized field integrating the principles of engineering and science. Fire safety engineering in particular plays a significant role in building design. It's all about anticipating the potential risks and mitigating them beforehand. This includes the use of fire-resistant materials, the implementation of fire detection systems, and the incorporation of safe evacuation routes. Now, let's take a look at some significant fire incidents that have shaped our firefighting strategies. The Great Fire of London in 1666, for instance, led to the introduction of fire insurance and the establishment of organized fire brigades. More recently, the tragic Grenfell Tower fire in London in 2017 has prompted a re-evaluation of building regulations and materials used in high-rise structures. The Triangle Shirtwaist Factory fire in New York City in 1911 served as a stark reminder of the importance of fire safety measures in the workplace. This incident led to significant reforms in labor laws and improved safety standards across industries. Each of these incidents, though tragic, has provided valuable lessons, shaping our approach to firefighting and fire safety. Today, firefighting techniques are not just about reacting to fires, but also about preventing them. This includes educating the public about potential fire hazards, promoting safe practices, and implementing stringent building codes. Technological advancements have also led to the development of sophisticated fire detection and suppression systems, drones for aerial surveillance, and even robotics for firefighting operations in hazardous environments. However, the fight against fire is far from over. With the advent of new materials and technologies, fires are becoming more complex to manage. But with our continued learning and innovation, we rise to the challenge. Firefighters are constantly trained in the latest techniques, and researchers are continually seeking more effective ways to prevent, detect, and extinguish fires. As we continue to learn and innovate, our approach to firefighting becomes more efficient, ensuring a safer future for us all. Fire, a force that once shaped civilization, is now something we shape and control. And while the battle is ongoing, our resolve remains unbroken.